What specific problem does the USACO benchmark aim to solve in the context of language models and competitive programming?
The USACO benchmark aims to address the need for more challenging benchmarks in the domain of language models and competitive programming. Specifically, it aims to provide a comprehensive evaluation platform that reveals the limitations of existing models and inference methods, while also offering actionable insights for improving algorithmic reasoning in language models. The benchmark consists of 307 challenging problems from past USA Computing Olympiad competitions, each requiring a wide range of algorithmic, mathematical, and common sense knowledge, as well as grounded and creative reasoning. The problems in the USACO benchmark are carefully crafted to assess a model's ability to reason about complex scenarios, create novel algorithms, and solve tasks in fictional environments. The benchmark goes beyond simple program synthesis tasks and focuses on evaluating models' abilities to reason creatively in grounded problem environments, which is a crucial aspect of well-rounded reasoning. Overall, the USACO benchmark aims to push the boundaries of language models' algorithmic reasoning capabilities in the context of competitive programming by providing high-quality test cases, problem analyses, and auxiliary resources for comprehensive evaluation and improvement.
How does the proposed method of combining retrieval and self-reflection maximize performance gains in the USACO benchmark? Illustrate step by step.
The proposed method of combining retrieval and self-reflection maximizes performance gains in the USACO benchmark by leveraging the strengths of each technique in a step-by-step process. Firstly, the model is prompted to solve the problem and generate an initial solution, which is then used in the retrieval query. The retrieval query includes the problem description and the initial solution attempt, which is fed into a retrieval function to retrieve relevant information from the knowledge store. This retrieved information is then inserted into the context to aid the model in the solving process. Next, the model engages in self-reflection by iteratively improving its generations based on the execution feedback of previous attempts. The model reflects on what went wrong in the previous solution, fixes the code, and incorporates the execution output of the previous solution, as well as information from a buffer of past solve attempts. This process continues for a set number of debugging steps, with the previous attempts and results added to the buffer after each iteration. By combining episodic retrieval and self-reflection, the model benefits from the external knowledge and reasoning provided by the retrieved information, as well as the internal iterative improvement process of self-reflection. This synergistic approach allows the model to learn from past mistakes, incorporate external knowledge, and refine its reasoning and code generation iteratively, leading to significant performance gains in solving the USACO benchmark problems.
What are the theoretical or practical benefits of using Retrieval Augmented Generation, RAG, in the context of coding domains?
The theoretical and practical benefits of using Retrieval Augmented Generation, RAG, in the context of coding domains are significant. The paper demonstrates that RAG can reduce hallucinations and improve reasoning capabilities in various domains, including competitive programming. By curating semantic and episodic knowledge stores for retrieval, models can access task-specific algorithms, facts, concepts, and past experiences to aid in code generation. This allows models to ground themselves in relevant problem environments, borrow existing code structures and algorithms, and utilize algorithmic concepts from texts. RAG enables models to generate more accurate code by referencing past solutions and reasoning, leading to improved performance in solving complex coding problems. Additionally, the synergy between episodic retrieval and self-reflection techniques can further enhance model performance, showcasing the potential for RAG to significantly boost the reasoning abilities of language models in coding tasks.
How were the models evaluated in the human-in-the-loop setup, and what were the key findings from the study?
In the human-in-the-loop setup, The models were evaluated by engaging in a multi-turn exchange with a human who provided feedback on mistakes without giving specific fixes. The human was only allowed to give general instructions, such as pointing out the incorrect algorithm being used or warning about potential errors like index out of bounds. The model then had a limited number of attempts to fix its mistakes based on the feedback received. The key findings from this study were that GPT-4 significantly outperformed GPT-3.5 in incorporating human-provided feedback. Specifically, on a subset of 15 problems where both models initially had a zero pass rate using all inference time methods, the human-in-the-loop setup raised GPT-4's performance to 86.7% with 13 problems solved, while GPT-3.5 remained at 0%. GPT-4 demonstrated the ability to pinpoint accurate algorithmic fixes in response to minimalistic feedback, while GPT-3.5 consistently provided irrelevant fixes despite the feedback given. This study highlighted the emergent potential of stronger models like GPT-4 to incorporate high-quality feedback effectively, emphasizing the importance of developing methods to generate human-level corrective feedback for improving model capabilities in algorithmic reasoning.
What are the limitations or challenges identified in the paper regarding the current state of language models in solving Olympiad programming problems?
The limitations or challenges identified in the paper regarding the current state of language models in solving Olympiad programming problems include 1. Limited algorithmic reasoning. The paper highlights that even the best language model, GPT-4, only achieves a zero-shot pass rate of 8.7% on the USACO benchmark, indicating a significant challenge in algorithmic reasoning for language models. 2. Inability to solve higher difficulty problems, weaker models like GPT-3. 5. CodeLlama and DeepSeeker cannot solve any problem above silver difficulty, while newer models like GPT-4 struggle with near-zero pass rates for gold difficulty problems and above, indicating a difficulty in tackling more complex Olympiad programming challenges. 3. Algorithmic errors. The paper notes that most errors made by models are primarily algorithmic rather than compilation errors, suggesting a need for improved reasoning and problem-solving capabilities in language models. 4. Temporal effects. The study shows that when evaluating models on problems released after training cutoff dates, the solve rate drops to 0 for all models, indicating a challenge in adapting to new and increasingly difficult problems over time. 5. Unsolved platinum problems. Despite improvements in solving gold-level problems, platinum problems remain unsolved by language models, posing a significant challenge for future inference techniques and model development. 6. Memorization versus critical engagement. The paper addresses the hypothesis that the success of retrieval methods may be attributed to memorization rather than critical engagement with the retrieved content, highlighting the need for models to deeply engage with problem-solving strategies rather than simply memorizing solutions. 7. Need for human-level corrective feedback. The human-in-the-loop study reveals that GPT-4 significantly improves its performance when provided with human-level corrective feedback, indicating a limitation in the model's ability to self-correct and adapt without external guidance. 8. Model misunderstandings. The study shows that GPT-3.5 often hallucinates fixes irrelevant to feedback, while GPT-4 can pinpoint accurate algorithmic fixes in response to minimalistic feedback, suggesting a challenge in model comprehension and response to feedback. 9. Importance of evaluation metrics. The paper suggests that current evaluation metrics like PASIT-K may not fully capture the capabilities of language models, emphasizing the need for better metrics to assess reasoning and problem-solving abilities beyond simple execution success. 10. Unlocking model capabilities. The results indicate that GPT-4 may have further reasoning capabilities that can be unlocked by human-level corrective feedback, underscoring the necessity for methods to generate and incorporate such feedback to enhance model performance in Olympiad programming tasks.
What are the key contributions of the paper in terms of introducing the USACO benchmark and testing LM inference methods for competitive programming?
The key contributions of the paper in terms of introducing the USACO benchmark and testing LM inference methods for competitive programming are as follows. 1. Introduction of the USACO benchmark, which consists of 307 challenging problems from past USA Computing Olympiad competitions, providing high-quality test cases, problem analyses, and auxiliary resources for evaluating language models, LMs, in competitive programming. 2. Construction and testing of LM inference methods for Olympiad programming, such as self-reflection and retrieval, to enhance performance in solving the USACO benchmark problems. 3. Demonstration that a combination of retrieval and self-reflection techniques significantly boosts LM performance, although current methods are still far from solving the benchmark above bronze level. 4. Conducting a novel, human-in-the-loop study to characterize the capabilities and limitations of LMs for Olympiad programming, revealing the potential of stronger LMs to incorporate high-quality feedback and the need for new methods to generate human-level corrective feedback. 5. Providing a comprehensive evaluation of LM performance on the USACO benchmark, showcasing the challenges faced by current generation models, especially in solving gold and platinum difficulty problems. 6. Highlighting that most errors made by stronger models in competitive programming are algorithmic in nature, indicating the need for further advancements in reasoning capabilities. 7. Showing that temporal effects and problem release dates impact LM performance, with newer problems posing increased difficulty for models. 8. Introducing and testing novel inference time techniques such as self-reflection and retrieval augmented generation, demonstrating their effectiveness in improving LM reasoning and problem-solving abilities in competitive programming. 9. Revealing the synergy between episodic retrieval and self-reflection techniques, leading to significant performance gains in LM solving capabilities. 10. Emphasizing the importance of human-in-the-loop guidance in enhancing LM performance, showcasing how human-provided feedback can unlock further reasoning capabilities in models and improve problem-solving accuracy.